As he said, I'm an emeritus professor. So this is I'm not a blockchain guy. So if you want blockchain questions, wait. I've been told that there's going to be a blockchain discussion shortly, everything like that. I'm also not a physicist. I'm not an electrical engineer, and I'm not a chemist. But I will say a lot of things about those that other people have told me are true, and I take them to be true. Okay, so what are we going to do today in the next little bit of time? And by the way, this is, to me, a topic that's incredibly exciting. It's one reason I left the university. But I'm going to be talking about it at a fairly high level because we only have an hour and there's a lot of stuff going on here. So like I said, either ask me if it's a burning question or hit me up later. So I'm going to start with the message, and you'll know what the message is in a minute. That's the thing that I want you to take away. If that's not, blazingly obvious. I'm going to talk about the renewable transformation more generally, but specifically in Texas, because Texas is a really interesting place vis-a-vis renewable power and electrical markets. Do I have to point this somewhere? It must be IR. For those of you who didn't take Econ 101, I'm going to do a little short briefer on economics, hopefully it's not insulting. It's not intended to be, but I just need to get a couple things across. Yeah. Then I'll be talking about some of the challenges of renewable power. I think we're all pretty familiar with some of them, but there may be some that you're not familiar with. And I'm going to talk about how controllable loads can help stabilize the power grid and allow us to onboard more renewables. And that's sort of one of the things I'm really interested in talking to you about, is how the fact that we have a controllable load will let us bring on more generation. We're going to use computation as a controllable load. You could use anything as a controllable load, but the fact of the matter is the controllable load has to have certain characteristics. And those characteristics are things that we can do with computers that we can't do with, let's say, an arc furnace or something like that, that also consumes a tremendous amount of power. And then I'm going to, this is the one I forgot to take. I'm not going to talk about our data centers in Texas, so ignore that slide, that bullet. Okay, let's get started. Another before we get started, these are just a few factoids that are important to keep in mind. In 2019, the EPA estimate for the United States is that on average, the generation of 1 megawatt hour of power, that's 1 megawatt for 1 hour, leads to the emission on average across the whole United States of 0.7 of a metric ton of CO2. Okay, that's every single hour. So that basically means on average, over a year, if you have a 1 megawatt data center, and a lot of my friends do, that means your data center on average is going to emit, cost to be emitted 5,000 metric tons of CO2. Now that's a lot of CO2, okay? It's less in Texas, as we'll see, because Texas has a different energy mix than the average in the country. Let's be clear why I'm here discussing renewables. It's really for two reasons. The first one is CO2 mitigation, and the second one is cost, because it turns out it's actually cheaper to use renewables than it is to use natural gas and other things. In the power grid, this is another little factoid that some people don't understand. I want to make it clear. The supply always has to equal the demand. So it's not like a widget factory where I can produce a bunch of widgets, store them around, and let them be taken out later. It always has to balance. Okay. Otherwise, bad things can happen. And that's what the physicists and EEs tell me, and I'll explain some of those. Okay, what's the message? Renewables today are the least expensive way to produce electricity in the world, period, full stop. Okay? And I'll give you some citations for that later. By the way, there's a lot of things I'm going to put up here. This is not an academic talk where I very carefully have citations and blah, 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 blah. I did that for a long time. If you have a question about where I'm getting any of the numbers, send me a slide number and what you want to know, and I'll go to the people who did it. But the vast majority of the data I'm going to show you comes straight from ERCOT. That's your grid provider, in case you didn't know that. Okay, so the pace of renewables that are being deployed really blows my mind. I grew up in the 70s where nuclear power was going to be so great, it was going to be too cheap to meter, blah, blah, blah. And a typical power plant we would talk about would be a 1 gigawatt facility, and they turned out to cost a lot more money than we thought. So, but right now, the rate at which we're deploying renewables just in Texas is staggering. And if you look worldwide, it really is amazing. It's gated primarily by the ability to get it engaged in the grid in a safe way. Controllable loads, particularly those that can rapidly ramp up and down, or what me and my guys at the office call dance with the grid, are really critical to maintaining grid stability in this kind of environment, in the presence of essentially non-constant wind and solar. I'm going to argue that computation can be used as a controllable load. That's the one thing I can tell you I know a lot is about how computers work. And we're building gigawatt scale data centers that provide inexpensive, mostly carbon-free electricity for computation, although with a quality of service arrangement that means you don't have it 100% of the time, because if you need it 100% of the time, then you have to have gas plants and stuff like that. Okay, so let's look at the transform. So this is the one thing citation I'm going to give you guys, is wind and solar are now the least expensive way to produce electricity. And there's a lot of reports on this. This is the LCOE, which covers capital and all that kind of stuff. But at the end of the day, it's also intuitive. I mean, essentially, your primary costs are your capital costs up front. And after that, you know, the marginal cost to produce solar energy is essentially zero. I mean, there's maintenance costs and stuff like that. This has led to an explosion. And the next couple of graphs are going to show you that in regions that are conducive to solar and wind power. In other words, Texas. And it's led to some challenges for grid operators, including in Texas, and we'll be talking about that. Okay, so renewables are exploding. This is partly because you guys have lots of wind and you have lots of solar, and my day in Austin has taught me that even in Austin, you have lots of wind and lots of solar. But when you get up in the Panhandle, they have more wind and more solar, and it's very, very hot. And it's also because Texas has a pretty unique market structure. The Dakotas have tremendous wind, not so great solar, but they have issues because they're a certain type of utility structure that makes it harder to do things. Let's just keep it like that. So we're going to look at Texas and ERCOT in more detail. This graph is right out of ERCOT. This is not the most recent graph from ERCOT. I would have had to have done recolor coding on it, and I decided I would show you data that was a little bit old, because the shape of the curves is what really is the important thing. Back in 2000, there was 160 megawatts of wind capacity in Texas, which is nothing to write home about. And you can see the growth rates over the last several years have been, truly amazing. I spent my early career in microprocessors when they came out, and we had 53% year-on-year performance improvements. Those were the go-go days in computing. This is the go-go days in renewables. Things are just really exploding. And you can see that the solar is also beginning to build out really fast. And the difference between the two different colors of yellow basically boils down to whether some contractual stuff has been done with posting bonds. And so you don't have to really worry about that. But you can see that the total capacity is 60, is going to be 60 gigawatts very soon now, which is pretty much what Texas uses. Epsilon, hot days, cold days, stuff like that. Now, I want to stress something here. This is capacity. In the computing business, this would be called guaranteed never to exceed. Okay, this is the max you will ever see out of these systems. You will not see that every day. And that's one of the important things that we're going to have to deal with. And so you typically talk about capacity factors, which is on average, what percentage of your capacity do you get out of a system? And the capacity factors are around, now I'm going to pick the wrong number. It's below 50%, but I think it's in the upper 40s. And I should have gotten that in my head before I came. Let's look at ERCOT's energy mix. Now, this is generation, not capacity. So generation says who actually produced the power in any given hour, as opposed to what generators were available to produce the power. And it starts back in 2007. And you can see over the last 15 years, wind has gone from essentially 3% of the mix to 24% of the mix. That's a pretty significant transformation. Sorry, I didn't want to fall down the stairs. At the same time, solar is just starting off, but it's also on a rocket curve going up in terms of deployed energy. Nuclear appears to be getting smaller, but that's only as a percentage. That's because the total has grown. You guys haven't lost any nuke plants, at least not to my knowledge. And then you see the gray, which is natural gas, which is the dominant life form. And then coal is really taking a pounding, going from the mid-30s% of power down to just under 20% of the power available today. This is also good because natural gas produces much less CO2 per megawatt hour than coal. And so, you know, if you care about CO2, that's a good thing. So this is what's going on in Texas right now on a statewide level. We're going to start focusing on a particular part of Texas, the part that really kind of excites me, and that's the Texas West load zone. We are not in that load zone here. And so what you see in this graph on the left-hand side is the average and peak utilization of load in the load zones. And on the right, you see what their generation mix is. And I encourage you to look at the West Texas generation part. And what you're going to see is that the yellow and the orange, solar and the wind, in terms of capacity, totally dominate West Texas, okay? The remaining bit in West Texas that's down there is basically one of the three common forms of generating energy from natural gas. So depending on the generator type, you have different efficiencies on natural gas. And that shows up in a couple of slides when we're talking about where the break-even price is on that kind of stuff. So we're going to focus on West Texas load zone and go from there. This is one of my favorite graphs. I have one from last year as well, but it includes Winter Storm Uri, and so it's a little bit scarier on the high end of the prices. We created this 2 weeks ago. For the Texas West load zone. And basically, the way this graph is formed is we take all the average prices, energy prices in the Texas West load zone every day, and you put them all down, and then you sort them by value, and then you basically chart them going out, right? So basically, what you're seeing is a very small percentage of the days this year so far have had high energy prices in that load zone. In fact, only one day has there been significantly high energy prices so far. That could change. The other thing to note, and this is another very interesting thing, you notice that there are a number of days, 15% of the time, in fact, where the price was negative. Okay? This fact that prices for electricity are going negative is what got the founder to sort of start this company, because there's graphs that you can look at produced by NREL, the National Renewable Energy Lab, that show the number of negatively priced energy days in load zones across the United States. And in 2013, there were only a few. And by 2017, there were a lot. And by 2019, whole swaths of the Great Plains were basically blanketed with negative energy days. And that's because we have so much surplus energy that they want to get rid of it, and they'll pay you for it because they get a small subsidy from the federal government for every megawatt hour that goes into the grid. They can't produce the power and ground it out. It has to be used. And so in order to get that subsidy, they'll give it away to get the subsidy back. Okay, so two other things to notice on this graph. The laser. So one thing to notice is here, I've drawn in, and by the way, these are for the natural gas prices last week. The price of natural gas, as you know, dropped significantly in the last 48 hours because of an explosion some damage at a liquefied natural gas facility in Houston, which meant that I think it was 16% of our exports are now basically natural gas are kiboshed until sometime later this year, which means suddenly there's more natural gas in the United States. So the natural gas prices have fallen, but basically for the three generator types, you look at the break-even price for the gas that says you have to sell the electricity for at least this much or you're going to lose money, right? So, you know, the marginal cost is higher than the marginal revenue. So what that can lead one to believe is that for a significant part of the time in the Texas West load zone, the power is coming from renewables predominantly. I didn't mention this before. When I talk about energy cost, I'm not talking about what your bill is. Your energy bill typically will have four things in it. It'll have an energy cost. It will have a transmission cost. It will have a distribution cost, and it will have taxes, fees, and other garbage. And we're looking just at the energy prices here, not at all those other things, which are artifacts of the system that we use. Okay, so at least to me, that graph just sings out opportunity because the electricity is really cheap. Okay. Again, there we go. Oops. Econ 101. We've all seen supply and demand curves. I want to stress that this is just a canonical supply and demand curve. It isn't meant to show anything in particular, right? It's what you saw when you were a freshman or a sophomore and you were taking micro. So this is a typical supply and demand curve. In your intro econ class, they treat them like they're carved in stone and they don't change. The fact is, depending on the product, these supply and demand curves can shift almost continuously. So for example, if the demand curve, and as we'll see in a moment, this isn't what a demand curve looks like for electricity, but if your demand curve was for electricity, you would expect the I should go forward one. You would expect the demand curve to shift to the right if it's a hot day, because people want more energy. And if it was a cooler day, it might shift to the left. And similarly with the power supplies, if a bunch of capacity were to drop offline, you'd expect the supply curve to shift to the left. So these aren't carved in stone, but they make a big difference because the revenue that the seller makes is basically the area under, you draw a box from the current price to the quantity, and that area is essentially what their revenue is. And at the end of the day, the people who build wind farms and solar farms are doing it for the money, right? I mean, they got to make money or they're not going to do it. Okay, let's look at electricity demand curves. They tend to be more what's called inelastic. That's a fancy term that says that it's really steep and that people's behavior doesn't change very much when you change the price. Their demand is still going to stay high. Certainly most people don't, sit around at home waiting to see what the energy price is right now to decide to turn on or off the AC, right? I mean, that's just not the way electricity demand works. And, at a supercomputing center, typically, you don't care what the energy price is. You're going to run your machines, and that's just what you're going to do. The supply curve can move around a little bit. So this is basically saying, in other words, demand doesn't generally drop much if it gets more expensive in the short term. In the long term, people can change their behavior. They get a different air conditioner. They decide the kids don't really need air conditioning and they should go outside and play in this, whatever. But in the short term, behaviors don't tend to change. Okay, so now that was my little backwards because this notion of inelastic demand curves and the revenue being equal to essentially that area in the box is going to be important in a little minute. Okay, so what are the challenges with wind and solar? And I would bet you dollars to donuts that everybody in this room could name at least one of the major challenges with wind and solar. What is that? So we got two. Transmission is one. Yeah, storm. Yeah, I mean, basically the wind doesn't always blow and the sun doesn't always shine, right? That, and transmission, somebody said, when I was teaching operating systems, I had a bag of candies. And what I would do is if you got a right one, I'd throw it at you. And if you were asleep, I'd do the same thing and try to hit you on the head. Okay, so the challenges are exactly what you would think. So let's go through them. The first one is congestion. And this is the one who said transmission. The problem is that the people, the industry, don't tend to be where the generation is. And you have to get the power from A to B. And if you don't have the wires to do that, or enough wires to do that, then we say that the lines become full, they're congested, and that means we can't push any more power across those lines. So that's a major power. Then, of course, the one everybody can figure out, they're variable and intermittent. The sun, the sun is diurnal, and the wind varies quite a bit. And the wind has some trends. They're strong. The winds tend to be stronger in the winter and tend to be stronger at night. And the reason is the same for both of those. And I'll just explain it really quickly. If we lived on a planet with no sun, but yet the wind still moved, then we would have what's called laminar flow across the surfaces, which basically means the air runs really smoothly. And so that it's going to be running at very high velocities with very gradual gradations going up. And the problem is we don't live on well, actually, it's good we don't live on a planet with no sun. But the challenge is that if you have a sun, when it's shining, it heats up the ground and the ground heats up the air, and that causes the air to rise, which is thermals. And by the way, I'm a glider pilot, so those are great. But as it rises, it causes turbulence, which disrupts the flow. It adds drag. And to make a long story short, the closer to the ground during the day, the wind is getting slowed down because of the laminar flows broken. Another little factoid, and I was trying to figure out where to fit this in, and I'm not a physicist. I want to emphasize what I'm about to say. I'm not a physicist. People have explained it to me again and again. So first off, the load and the supply are always the same, but they vary sometimes a little bit. And as they vary, it can cause changes in the frequency. You all know that you have a grid that's nominally at 60 hertz. So, and don't push me on this one too hard. So basically, if the load starts going up higher, what's going to happen is the frequency is going to start to drop. And as the frequency drops, the generators try hard to keep it up, essentially using literally the inertia of the spinning magnetos and the wheel and all that stuff that's on it. And the current starts to rise. At least that's what they keep telling me. So what happens is the temperature starts to go up, and in a very short period of time, the equipment will start to get really hot and will destroy itself. So the operators of these transmission stations don't want this to happen for pretty obvious reasons. So what you have to do is get the frequency back in line. So what happens is they get, if I'm a generator and the frequency is dropping and my machines are about to be destroyed, I'm going to pop myself offline to prevent that from happening. And when I pop myself offline and I'm a generator, what just happened to the grid? The frequency is going to fall some more, and it will cascade, and pretty soon you'll have a dead grid, okay? So what the operators are going to do is they'll black out Austin, or they'll black out Houston, or they'll black out somewhere to drop the load, to bring it back into balance, okay? So nobody likes blackouts. I'm pretty sure about that. In fact, person I was sitting, we were talking about the last time we had a power failure, right? So nobody likes those. So the grid operator, in your case, ERCOT, keeps a huge amount of spare capacity online that can be brought online really fast. And it has to be brought on really fast. The most important kind is called primary frequency response. It's responsible for bringing the frequency. Is this too technical? I taught an intro class to computers for poets a long time ago. And one of the most earth-shattering things that I learned during that, when I was trying to talk about the exponential improvement in processor performance, is none of the kids knew what exponential meant or logarithms. And I can't tell you how sad that makes you feel. Anyway, where was I? All right, so they have the spare capacity that they can bring online at any moment to do primary frequency response. And that means they either have to add more generation or drop some load. Dropping load is equally good to adding more power, because all you're trying to get is back to the balance, okay? So they also have reserve capacity in longer time periods, like 15 minutes, which may seem like a short time to you, but in the grid world, that's really fast. And then more slowly up to 3 hours, okay? And they basically pay people to have this capacity online if they need it at the drop of a hat. And as I said, it's either an increase in generation or a decrease in load. Okay, so that's the problem with, and that can be driven by the fact that these things are variable. And we're going to look at that more in a second. So then there's congestion. We already talked about the, oh, I went the wrong direction. Oh, no, I didn't. Right, I forgot the battery piece. So at the end of the day, you need to have a lot of energy storage systems, or the ability to rapidly shed load or add additional capacity. And a lot of people think batteries are the future, and they are, but they're not now. Because battery storage, it's not even that it's so expensive. The total production in gigawatt hours of storage capacity in the United States isn't enough right now to even give Texas 5 hours of capacity if something failed, if all the generators failed, because you have to take the gigawatts that you need times the number of hours you're going to be down, and that gets gigawatt hours, and that gets really expensive really fast. There are systems like that in the world. They're the most popular kind that's most effective are what are called pumped storage systems. They're used around the world. Austria is called the battery of Europe because in the Alps they have all these lakes at different levels, and when they need power, they let it fall down the hill, and when they have plenty, they pump it back up the hill. And it's really fascinating to visit some of these places. Many of them were built before the war, and for a person of my age, that means the war, World War II, and they've been around for a long time. Okay, so let's go on. This is a nice snapshot of 3 days in Texas. And what you can see is the load is sort of the top, and it's sort of predictable. But what you can, and by the way, non-renewable is slightly a misnomer here because that includes nuclear power, which in my mind is a renewable resource. We'll get into the fight about that later. Jay's giving me the hairy eyeball. So you can see that the wind and the solar are kind of going up and down all around, and essentially the natural gas and other stuff has to pick up for that. Okay, I'm going to skip frequency stability because I'm now behind on time. But to make a long story short, frequency stability basically means that's the blue line right there is the frequency of the grid. When the frequency suddenly drops, this happens to be from a data center we were controlling with 54 megawatts at the time, and that's our power consumption. And as soon as the power drops, we drop. And that's called PFR, primary frequency response. And that's what you have to do, 15 seconds or bust. And I'm not going to go into it in any more detail, so I'm going to skip through all this stuff in the interest of time. So let's talk about congestion, which is what Sudafed is for. And this is actually one of my favorite sets of slides that the company has, because this to me completely and totally highlights what's going on in Texas. So on the left is what's called the nodal heat map, which is basically a fancy way of saying at each of the at each of the generators, we're looking at the average price of energy over the year. And each little dot is somewhere that was generating power. And what you can see, I don't know if you can read those numbers, but basically it's really cheap up here. Wrong button. I got to point that way. Go backwards. Versus foil again. See if we can go forward. Okay. So what you could see, and I'm going to hit the right button this time, is up here, energy prices are really low, and down here, they're much more expensive. And you're asking yourself, gee, why is that happening, right? Why do the people up near Lubbock get such cheap energy? They get such cheap energy. Those of you who took graph theory math classes can now say, I'm utilizing what I learned 30 years ago. If you look at the Texas grid, it's a graph. There are nodes and there's edges. There's a cut in that graph that separates Texas West from the rest of Texas. It's right there. If you're on the left-hand side of that, you're in what's called in graph theory a clique of things that can communicate, in my world to be communication, or move power around very efficiently. If you have to cross the cut, there's a finite amount of capacity that can go over that cut. It happens to be that finite amount is somewhere between 12 and 15 gigawatts. Depends on things that I don't fully understand where it is either way. And if you're in the southern part of that, or southeastern part, there's only a certain amount of power that can come across that. So even if there's 100 gigawatts of power in West Texas, it doesn't matter. Only somewhere around 15 gigawatts can make it out, okay? And that line is called the Krez line. And Jay asked me what that meant last night, and I couldn't remember, and so now he's going to know. I'm beginning to, no, it's just slow, that's it. So Krez line stands for Competitive Renewable Energy Zone. I didn't make that up. And basically it was built by the state of Texas to once and for all take care of the energy imbalance problem. It was very expensive. It's very expensive to build these lines. And to make a long story short, what we have is in 2021, we had over 25 gigawatts of renewable capacity up there. Plus, as you might recall from earlier, 4 gigawatts of essentially natural gas. And what happens is we're building more and more renewables up on that other side. And when the wind is really going and the sun is really shining, all that energy can't get out. Okay. And so I like to think of it, it's just being spilled on the floor because we can't use it. And that's a waste. And that's what leads to negatively priced energy, is people want to get rid of that energy. And the only way they can do it in an open market is make their price the lowest price, negative price. Okay. So there's our export limit. And this, in a nutshell, is sort of why our company exists. There's all this power up there. It's going to waste. What can we do with it? Okay. No questions. Great. Okay. Let's go forward. Okay. So congestion leads to something called curtailment, which is basically a fancy word for being told you can't produce any more power and you got to reduce how much you're doing. So when a generator is told not to produce energy, they're being curtailed. It happens all the time. I used to wonder when I drive around why 3 of the turbines on a giant farm are turning and the rest aren't. They've been curtailed, right? So you have an opportunity to produce the electricity, but you've decided not to do that because you can't do anything with it. Generators, and this is important. Let's think back to Econ 101, right? The generators don't get paid for power they don't sell. They do get paid for power they sell. So when they get curtailed, their revenue is being reduced. Pure and simple, right? Keep that in mind. So it makes renewables less profitable. And the whole, as I said before, you know, their business is to make money, not do social services. Okay, so, and also, and this is more my take, it's a waste of power. It's a waste of power that didn't cost us anything to produce and doesn't really generate any carbon dioxide. And yet we're letting it just slip through our fingers. Surely there's something we can do with that. And when anybody ever asks you a question like that, the answer is yes, of course there is. Or you're playing, what's that movie, Airplane? Stop calling me Shirley. Okay, so second problem, intermittent output. The wind doesn't blow, the sun doesn't shine. Let's look at that. I'll bet a bunch of you have solar rooftops. No? Yes, no, maybe? Have you ever looked at your power output function over the day? When I look at mine at home, I can tell every time a big cloud passes overhead because it goes like that. Okay, so let's see if we can, there we go. This is a wind power production function for a wind farm, 150 megawatt wind farm near Lubbock. So what we're looking at is the power production over a couple of days. It doesn't really matter when or where or anything like that. But what you can see is it's going boom, 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 up and down. The blue line is essentially when we can expect a certain amount of power out of that. Another way to take that same data over the entire year, which is more useful for planning purposes, is to look at, and right here, what we're looking at is the total power output production, and this is the percentage of hours that are above that point. So basically, what you can see, just to make it, you know, crystal clear, a very, very small percentage of the time, we're operating at a full 150 megawatts. Remember, I said you don't really get full capacity very often. But the converse is we're getting a good 5 or 10% of the output 90% of the time. Okay, so you're usually getting some power. It's not a Boolean up and down kind of thing. The only question is how much. This is going to feed into a chain of logic I hope to stitch together for you in a minute. Okay, so this is the power can vary rapidly. That's the message of the top one. And then you do end up with these nice distribution functions, which help you from a planning purpose to understand what power levels are going to be available, what percentage of the time. And this is important if you're going to build something that depends on that. Okay, next slide. The other thing, the dates don't matter for this. This is just something that we pulled from ERCOT. Remember I said that wind is better in the winter and better at night. So these two graphs on the left-hand side, we're looking at across all the months on the average amount of load. And the first thing you'll notice, and this is for Texas, you'll notice that, gee, the load is higher in the summer. You know, what a surprise. There's air conditioning, right? That's basically where your load goes. Sadly, wind production is worse in the summer. Okay, that's a bummer. At the same time, if you look at it over a 24-hour, typical 24-hour cycle, the load is higher during the day. That makes perfect sense to me. But then the wind production is lower during the day. Now, fortunately, solar complements that, because solar, the production is higher during the summer and lower during the winter, and it's higher during the day and zero at night. And so they complement each other really, really very well. Okay, and then you have problems with the edges of when that's happening. I'm having a hard time getting this to click. There we go. So the challenges that we had are, I'm here. Okay. So how are we going to address these challenges? So what we're going to do is we need to move the load closer to production. That's the first thing that we need to do. And I, by the way, grew up in a rural community. And the thought of moving more industry to rural areas sort of makes my heart swell with happiness, because maybe, we'll do something about, chronic rural employment problems. But anyway, let's not go there. Okay, so we need to move the load close to production. So there are a lot of industries that suck down huge amounts of power. I mentioned arc furnaces earlier. There's all kinds of things that use a lot of power: aluminum, heavy manufacturing, computing. Okay. But most require a lot of infrastructure in order to do that. You don't just build an arc furnace in the middle of nowhere. You got to have a transportation network to move stuff in and out. You have to have a population to do all that kind of stuff. It just doesn't really work out. Turns out computing doesn't. I've been in this business a long time, and we basically need two things in a data center. We need electricity and we need networking. That's all we really need. We need a few people, but one of the things that's been happening over the last 20 years is remote management of machines has become the norm. Okay, so you need fewer and fewer data centers. Those of you who've been in a hyperscaler facility, the first thing that strikes you as you walk down the aisles is you don't see anybody. Okay, they're basically abandoned. They're not abandoned. There's no need for people to be there. The second thing we want is a controllable load. We want to be able to ramp the load up and down, ideally within 15 seconds, so that we can help stabilize the grid. Or be able to bring them down when we don't think we're going to have enough power. So let's talk about flexible controllable loads. We want one that can ramp up and down on command. So one thing we could do is we could build giant toasters and place them in Texas, right? Why not? Now, that begs the question of, we could also just not produce the power. So you need to have some kind of load that's going to pay for the electricity, which is unfortunate because, and this is my one joke of the evening, I'm a glider pilot, and I can think of nothing better than a gigawatt or two of hot toasters somewhere heating the air up, and I could fly forever at 16,000 feet, right? But there aren't enough glider pilots who are willing to pay anything for that to ever make that happen. So a giant, multi-gigawatt field isn't going to happen. What we're proposing that one can do is you can use a giant multi-gigawatt compute load to soak up the excess power and pay for it. That's critical. And pay for it. This is going ahead without me pressing the button now. Wow, that's weird. Okay. So what you want to do with these compute loads is when the energy is there and it's cheap, you crank it up. And when it's not there, you just shut it down. The critical thing is it's a non-zero price, makes renewable generation more profitable. And what do people do when the ROI goes up on an investment? They build more. Okay, that's the way it works. Okay, and so then we'll have more renewable generation. And then you're thinking to yourself, wow, we'll just have a bigger surplus. Yes, that's true. But it also means at that time, when there's only 10% available, it's 10% of a larger base. So you're going to have more renewables all the time, which means you're not going to need as much of the gas plants to carry you over in those times. Okay, so we won't need as much brown energy and we'll be able to move forward. Okay, now let's see if I push the button if it changes. Right, I already said that. Okay, now I'm going to explain this graph, and this is where we're going to combine microeconomics 101 with a little bit of stuff here. The important thing is the shape of these graphs, not all the little text that's next to it. It was something I could find. So here is a nominal demand function for, we're going to assume here that the supply function is the same over time, because you can imagine the supply function shifting around too, and it doesn't change the story I'm about to tell you. Suppose that our traditional demand function is this vertical line or near vertical line. When we add in controllable loads of different types of computing applications, what we're going to do is we're going to have a demand for electricity, but only up to a certain price point, depending on what it is they're computing. So the idea is we've taken a normal demand function, which is near vertical, and we've added a bunch of additional demand where the demand drops in and out, depending on what the actual price is right now. So we now have a demand function that goes down and over. So for example, if it's a day where it's cool in Texas and the demand for electricity is low for electricity, we'll have a demand function with this supply function, and we may bring up to 10 gigawatts, and I'm making this number up, okay? 10 gigawatts of extra load that's there sucking down power and paying for it, okay? Then suppose the demand function changes because it starts heating up. And I'm making this up. Let's say this was 10 a.m. It gets hotter and hotter and hotter. The demand goes up. As the demand goes up, the price will go up. And these lower value computations will drop out of the market. They'll just shut the machines off, which means that we're essentially giving the power back, to the rest of the system. As the demand goes even higher, those other resources that were sucking down, you find a better word for that were consuming all that extra load, just get out of the market completely. And they're no longer impacting the overall load in the system. This is the most complicated slide here. Okay, what I'm trying to get across is we're going to change the demand function by adding additional load types that are price sensitive and can get out of the market, in and out of the market rapidly. Okay, when the price is low, they use more. When the price is high, they get out. And in my group in Charlottesville, what we like to say is when the power demand is really high, we're going to shut down the computers and let the humans have it. Because that's kind of what it boils down to, because the computers don't care if they're turned off. Humans care quite a bit if they can't get any electricity. Okay. So now we get to my part of the business, computation as a flexible load. And I'll talk about two kinds of computation. I forgot this. Sorry about that. Forgot my own sequence. Okay, so as a flexible load, when energy costs are low, energy costs tend to be low when renewables are going. I mean, that's when we see those negative price days right now. So we have three regimes of interest for our stuff. We have the days when there's plenty of power and it's go, go, go. Turn the crank all the way up and consume that power and generate revenue. As you start approaching the edge, then what's going to happen, there'll be real-time decisions, A, to stabilize the grid if that's necessary, but also to shut down due to price signals. So as the price signals tell us the energy is needed elsewhere, we get out of the market. And then the third one is there's a power shortage, prices are high, we're shut down, right? We're all but shut down. And the population centers don't have blackouts, ideally, unless it gets bad, and then you're no worse off if we were there or not because they're turned off and you're out of power. And you don't have to spin up as many peaker plants because we have a higher base of renewables. Okay, now, if you're in my business doing scheduling, and I've spent a lot of my life doing scheduling of high performance parallel programs and distributed systems, being able to accurately predict when that's going to happen is very valuable. And there's a lot of work actually going on right now around the world by Google, by others, to be able to accurately predict renewable energy generation on an hour-by-hour basis, because then that can be used to essentially know what's about to happen instead of reacting to what's happened to you. That's why the little smile. I suspect there'll be many federal grants paid for algorithms for that. And to be honest, I have a grad student right now finishing her dissertation on using reinforcement learning for predicting that, but let's not talk about that. Okay, so let's look at two types of computing, Bitcoin and regular. So Bitcoin, very popular. I'm not a Bitcoin guy. Let me tell you about it. The miners are on a Linux, which is an operating system, which many of you are probably familiar with. I'll tell Jay a joke about this later in a different company. I have a Red Hat Linux hat. It's certain political things in the past have completely contaminated what a red hat means in this country. And I was accosted for wearing that hat by somebody who can't read. Anyway, so 95% of the power consumption in a miner is in what are called the hashing ASICs. That stands for application specific integrated circuit. We can reduce the power consumption on a typical node type. I think these are S19s. It doesn't really matter. 95% by just turning off the hashing. So we go from 3,200 and change watts to 170 watts. And we can do that in under a second. Okay. Lancium has patents in this space. We've developed technology. We have this thing called smart response, which directly works with ERCOT to do frequency response and also base point setting, so that we can basically make those Bitcoin miners dance with the grid. Okay. And do it very, very quickly. And we can actually respond with frequency events to help stabilize the frequency. And I can assure you that the pricing, if you look at the graph I had a minute ago with those sort of multiple step functions, those correspond to different generations of miners that have different break-even points in terms of price of electricity. Okay, so we have patents. That's really great. Now let's talk about traditional computing. This is sort of my on here. Is this button stuck? Okay. Let's take cloud computing. I'm guessing most of you know what cloud computing is. That's where you have big data centers somewhere and you run jobs on them. So if we want to drop load in a cloud computing environment, we have to stop the jobs that are running on there. And we need to do that in a clean and consistent way. Because once we stop the jobs, if we can do what's called persist them, which is a fancy word for saying save them to disk, so we can restart them later, then we can stop the jobs and turn off the nodes. But the problem is you can't do this with all applications. You need applications that won't be able to tell that you turned them off and started them again later, ideally. You need these jobs that can do this, and so we can do what's called migration in space and time. And they also have to be jobs that are tolerant of delays. So that if the job ran for 2 hours and it was put to sleep for 2 hours, it should be tolerant of that fact, because otherwise it's not a good candidate. So this rules out, by the way, interactive applications like Netflix, right? Most of you, if you were watching a Netflix movie and it suddenly stopped, your response wouldn't be, gee, the grid is being preserved. Your response would be something else, right? So we're not going to do things like Netflix or anything like that because they need to stay on or they don't have any value. On the other hand, there are a lot of jobs that don't either need to be interactive or communicate with other jobs. And that class of applications is called high throughput computing. Why is this going ahead without me pressing? You're not doing that in the back, are you? You are? No, you're not either. This is just being done to make me look super silly. Okay, reminds me of my youngest son, who always is telling me mockery is the sincerest form of flattery. I'm not sure I believe that. Okay, so high throughput computing is really common in science and engineering and modeling and all other kinds of things, machine learning, et cetera. And basically, it's a set of jobs where the user doesn't really care about any particular job. They have a set of jobs, and they care about when the set is done as opposed to any given job. So what you can do is essentially, and another important feature is these jobs don't talk to one another, and they can run in any order. That means that we can pause and restart these jobs at will and not affect the correctness of the program. I know that sounds a little nerdy, but when you're selling a service to somebody, you don't want to affect the correctness of what they're doing. That's not what they want to pay for. So furthermore, unlike web services, they tend to be compute intensive, and we're actually looking for compute intensive jobs because they use more electricity. When the computer is running hard, it's fully saturated with load. It uses a lot more electricity than if it's just running a bunch of web servers that are ticking over most of the time and not actually doing anything. So there are lots of jobs in this space. Machine learning, particularly training, fits into this category. In fact, machine learning is rapidly becoming one of the biggest consumers of electricity in the computing world. It really consumes a lot of power, particularly because it tends to use a lot of what are called GPUs, which are particularly power hungry. Aircraft design, car design, all those kinds of things. And aircraft design is my favorite example. If I'm computing how a new wing performs, I want to understand how it performs at this angle of attack, 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 at 40 miles an hour, at 50 miles an hour, at 60 miles an hour, with the flaps at 10 degrees and at 20 degrees and 30, so on and so forth. Thousands of permutations of these, or parameter spaces it's sometimes called, need to be computed. 3D molecular modeling. I have a colleague who says that, chemists are the locusts of computing. They'll basically eat whatever they can because these 3D molecular models consume huge amounts of computing time and they take a long time to do. And we use them a lot in drug design. Similarly, graphical rendering. This is another application most people are familiar with. If you're watching a digitally animated movie, every single frame is a separate computation. And you have a lot of frames to do. And by the way, these frames all take different amounts of time may take different amounts of time to compute. In fact, they almost always do. So there's a lot of these. And then the one that always covers everything else is Monte Carlo simulations. Essentially, economic Monte Carlo simulations are simulations where you're just constantly rolling the dice to see what's going to happen next. Okay, so the drop load in this environment, and I promise I'll wrap it up soon. What we do is we migrate jobs in space and time. And in time means in order to manage load. What we do is we migrate jobs in time by putting them on disk, shutting off the node that they're on. Come on, come on, come on. And by turning the node off, we eliminate its power consumption. That should ideally be obvious. And then we restart them later when power is more plentiful or cheaper. In space, right, we move the job from one site to another site. What we basically do is we persist the job to disk, pick up that image or set of images that represent the job, what it was doing at that time, move the whole blob somewhere else, start it back up over there. It takes some time, but less time than waiting for the power to come back. It takes a lot of networking though. Trust me on that one. We can also, if we need to, really quickly, we can freeze everything on a machine in under 100 milliseconds. Now that only drops the load in about half, more if you have GPUs, but it doesn't really drop us down. The percentage isn't as high as with Bitcoin. And then finally, we can persist them, shut them down, and move forward. We can unplug the nodes, but there are technical reasons why you don't want to do that, primarily being that a lot of computers, if you physically disconnect them, they won't start back up again when you plug them back in. And I can explain why that happens some other day. Okay, conclusion. Now soon you'll be able to go home. What I hope you learned. Renewables are the least expensive way to produce energy in the world today. Look it up in the 2020 International Energy Agency report. If you don't believe me, believe them. The pace of renewable deployment is staggering. Every time I look at that ERCOT graph, it just blows me away. When I was a kid, adding 10 gigawatts to the US power supply was a big deal. And now you guys are doing that almost year on year, but not quite. I mean, it's really, really amazing to me. And that's just Texas. Controllable loads, particularly those where we can rapidly reduce them, are an alternative to having spinning reserves of carbon-based energy that we can ramp them up faster. It's easier to drop a load than it is to burn more energy. And also we can just pull our load off in order to give more energy back so that we don't have to start doing rolling blackouts if there's a problem. Computation can be used as that controllable load. That's what I do for a living. By the way, I'm going to add one. Lancium's building gigawatt scale data centers to do this exactly, although not with 100% quality of service on electricity. So we're basically inverting the model I grew up with in computing. Jay used to run a supercomputing center, and if you're a supercomputing center or a hyperscaler, you want 3, 4, or 5 nines of power availability. 99.9% on, 99.99% on, 99.99% on. We make the electrical grid meet our requirements. That has been the mantra of my entire career. What we're saying is we're going to flip that equation and make the data center adapt to the grid instead of the other way around. And by doing that, it allows us to use renewable power instead of carbon-based power and reduce the carbon footprint of our work. I've done supercomputing for well on 30 years. I've been traveling a lot the whole time. I have a carbon footprint you wouldn't believe. Okay, and so one of the things that we can do is try to take that carbon footprint of computing and move it up and reduce it. It can, and then we talked about how that can in turn, increase the amount of renewables by essentially providing a flexible load and giving them revenue to encourage them to invest. And now, this is a vision. This is sort of my vision of where we're going. This is a map generated by NREL, the National Renewable Energy Lab. This shows the wind energy potential of the United States. It's called the Great Plains Wind Belt. There is so much power there you wouldn't believe, right? It's just waiting for us to pick it up, okay? And the way that we can mitigate the risk of the wind not blowing in any particular region, if the wind isn't blowing in Lubbock and we have to, and I picked Lubbock at random, and we have to start shutting stuff down, we'll just migrate the load up to the Dakotas or to wherever there's power right now. The way I look at it, for regular computing as opposed to Bitcoin, we can essentially slosh jobs up and down the Great Plains on the fiber and move things around. And so we can move to very close to a net zero impact on for computing at least. If we get better forecasting, and we will, we don't have to do it reactively. Reacting to a change is more expensive in bandwidth because you have to move more state. If you know ahead of time that you're going to want to move something somewhere, you move it ahead of time. So the amount of data you have to state is equal to the amount of data you have to move is significantly reduced, which means you don't have to deal with as much bandwidth. And every megawatt computation, if you use the US numbers from 2019, every megawatt hour of computation that we move out of a carbon-rich state, and I'll pick the most carbon-rich state, West Virginia, we're going to reduce the amount of carbon we throw into the air. So a lot of the effect is also substitution effects by essentially saying we'll take a computation from here, we'll move it here. We no longer are emitting the carbon to run that data center there. We're going with wind and solar in the Great Plains. So this is my personal opinion. I want to stress this is not necessarily the opinion of Lancium. One of the reasons I left the university is I believe that we're entering a transformational era for industry in the United States, where we're going to be shifting from essentially a carbon-based industry and energy system and chemical processes system to one that's primarily based on electricity, specifically renewable electricity. And as we do that, that's going to have profound effects on society, technology and society, and everything else. And to me, it's essentially a new industrial revolution. And we're going to see a transformation as the wind belt and the solar belts, and we figure out how to adapt to these kind of energies and move more and more industry over. That's sort of why I'm in the game. And for your information, Texas is at the center of this right now. And you guys can be happy about that. That's why I spend so much time in Texas now and never thought I would. Thank you very much for your time.
That was perfectly timed. And now we have time for some questions, and they've been submitted to the Slack channel. For today's guest moderator for the Q&A, I am going to bring up the woman who helped us move the Austin Forum into downtown Austin, got us great venues, and really helped us in this transition from being something that appealed to lots of folks at the university, which we always want, and we love having our university attendees here, but achieved a broader audience in moving into central Austin from the tech community, from local government, et cetera. So please welcome Allison Warner, a former managing director of the Austin Forum.
Kind of a lot to live up to.
Great. I'm fine. I have to remember to kiss the mic.
All right. So what reception has Lancium received from Texas's leaders? The same who were blamed for renewables, or who blamed the renewables for the Uri grid failure. And that was submitted by Steve Grant.
So I feel like, you know,
Little touchy.
a little, yeah. So
We are non-political,
Yeah.
but
So I'm not the person in the company who deals with that, but my understanding is that the blame game I want to stay out of. We've gotten I think, very good reception from many Texas politicians about bringing Bitcoin specifically into Texas. Because it creates jobs and all of that kind of stuff. In terms of the details of that, I'm really not the person to ask. I know that sounds like a total cop-out, but it's the truth. And so I'm going to cop out. I'm a technical guy. Let's keep it clear.
okay. From Rishab Argawal. Is there a way and need to prioritize which computational jobs to stop first if the grid demand picks up and renewable prices increase? Does a job have some kind of associated value function?
He must work for our marketing team. Yes, there is. Essentially, the model that we have right now, we're running all our jobs at 100%, but the model that we've built introduces what are called qualities of service. So an end user can select, for example, a 95%. We never guarantee 100 because actually when you're starting up a job, it's not actually making progress. That takes time. So we can asymptotically approach 100%, but not actually achieve that. And then with that quality of service, you start running and we'll never turn you off. Never being a strong term. And then there's a 75% quality of service that basically says, once you start running, you will be on processor 75% of the time. Which means that if you had a 3-hour job, if it ran 100%, God, I hope I'm doing my math right, you know, it would take at most 4 hours, or a 50% quality of service, you're on halftime. So if you have a 10-hour job of runtime, we'll guarantee it will finish in 20 hours. And you get charged less for these different qualities of service. And as the scheduler, that's me, now I can put on my technical hat, you give me a lot more degrees of freedom to optimize the situation. And so that allows us to be able to, and then we have a best effort, right? Where basically we'll give you what we've got, and if it's no good, we take it away. So absolutely, in order to be able to do regular computing as opposed to Bitcoin, we have to have the ability to shut off jobs. And in order to do that, we have to tell the user, we're going to maybe shut off your job, because otherwise they'll be very disappointed when it gets shut off. But we will compensate them for that. And in that way, they choose the quality of service that they want. And by the way, if you pick 100% quality of service, your job may be moved to a place where the power is just straight up grid power, because we can't guarantee that otherwise. That's the answer to that question.
The next question is from Larry sorry, I can't read with my Ketcherson. Does the imbalance between West Texas and the rest of Texas exist in other states? And if so, do any have as big a difference like the slideshow for Texas?
Right. That's a really good question. And the answer is yes. Congestion is not just a problem in Texas. It's one of the primary reasons. I can't tell you some stories I've had with, I don't want to name the state because that will get me in trouble. But so Texas has a market-based system, which makes it really possible for us to do some of these things easily. I was talking to a power person in a state that will remain nameless, where they had a wind farm in that state, where the wind farm was being curtailed all the time. And so they wanted to cut a deal with us that we would buy that excess power. But because of the regulatory infrastructure in that state, they had to get approval from the state grid. And the state grid would set the prices that we would pay. And I literally had somebody in that state who ran one of these systems tell me he couldn't possibly let that wind power station charge us any less for electricity than the cost of the natural gas to produce it. Okay, and it's like, what? There is no natural gas involved here. You know, so there are many other states that have congestion problems, particularly in the Great Plains, but they're a little less realistic about how markets work. Let me just put it that way. And I'm not going to name the state because I have friends in that state and then I'll get in trouble. They know who they are.
Okay, another question from Tina Slivka. Can the West Texas surplus be sold to other grids?
You have the same problem. You got to get the electricity out, right? If we could get the electricity to the rest of Texas, you wouldn't have to sell it to other grids. I don't think, okay? But where are you going to, you know, I'm not a historian of ERCOT, but ERCOT was, to my understanding, originally formed so that it wouldn't have to follow federal rules, which meant it had no interconnects with other states, because if they had interconnects, it would be interstate commerce and they'd be subject to federal rules. That's what I believe is true.
It's not just because we're so big.
That's a Texas question. I grew up in Indiana. So I'm not, I don't think it's that, but I don't know. Yeah.
Okay. So the last question was my favorite question. And oh, shoot. Jeff Zavala. He is here. Okay, good. All right. So the question is, what impact can the average citizen make by adopting decentralizing energy production with microgrids? And is that effort still part of the equation of building a sustainable, renewable energy solution?
I haven't really, that's not my area of expertise. My gut tells me the answer is yes. But the one thing I've learned working on this project and working in Texas, where there's huge amounts of renewables, is all the stuff that my wife and I had done for years to reduce our energy impact and have all this other stuff is totally and utterly dwarfed by industrial scale energy production. So my heart wants to say yes. I don't know that as a fact, but when you're talking about so many gigawatts of power at industrial scale, I'm not sure the answer is yes, but I don't want to get into that. I don't have a dog in that fight, I guess is what I would say. Yes, sir. Machine, yeah, high throughput computing problems, yeah. So for the sound. Okay, so I'm supposed to repeat the question for the online audience. So I'm going to give you my regurgitation of that question as I best understood it. In my list of application areas, I listed AI and some other things. And by the way, that was a very short list, not a complete list. What about Bitcoin? And in Bitcoin, the questioner asserted that it's a race to get the answers, right? My understanding is that the important thing is the rate at which you do it over a particular period. And so in that sense, you're right. But nonetheless, for our customers, at the end of the day, electricity, so I'm going to give you kind of a roundabout answer as I understand it. Yes, they want to get as many terahashes as they can, because the terahashes that they get compared to the overall pool is going to determine. And once again, I want to stress I'm not a Bitcoin person, so I may have this wrong. They care about the rate. So what we do is we contractually, when we set it up for them, we tell them we will give you this percentage of power on. And if we fail to meet that, and by the way, you have to put your machines under our control so that we can pull them up and down their energy consumption. If we fail to meet that, we have contractually obligated ourselves to make you whole by certain mechanisms that I'm not at liberty to discuss. Okay. And that's what we do basically. And in return, they get incredibly inexpensive electricity, because when we bounce our power up and down, we're not just being good guys to help save the grid and keep it stable. Remember, I said that in all of the grids, they have these markets for primary frequency response, for 15-minute ready reserve, for 3-hour ready reserve. I have a whole slide on this that I didn't include, where the grid operator pays you to do that. And they pay you to be able to drop your load within 15 seconds. They pay you per megawatt hour, whether they ask you to do that or not. And by doing that, we can keep our price of electricity extremely low. And so anybody who's getting power from us, they know what the contract is, and I can't talk about those. And they're willing to do that because of the energy price that they get at the end of the day. And energy is the primary input. I believe energy is the primary input cost for Bitcoin mining. And so therefore getting inexpensive energy is worth more than another 5 or 10% of uptime. That's a long-winded answer, but I'm trying to set the context up.
Great. Thank you very much. Let's thank Jeff Zavala for his winning question, Allison Warner for her moderation, and again, Andrew Grimshaw for that informative presentation.